Good afternoon, everyone. This is Elisa Baum. I'm GridGain Systems Director of Product Marketing. I'll begin in just a moment, but I need to conduct a bit of housekeeping. Could you please let me know if you can hear me using the hand icon in the GoToWebinar control panel? Okay, let's see. You guys hear me? Yes, you do. Perfect. Next, during this webinar, you will be on mute, but if you have any questions during the discussion, please go ahead and enter them in the questions field within the control panel. And at the end of the discussion, we'll take time to answer as many questions as possible. I'll also send everyone's questions to Denis, our speaker today, and we'll do a follow-up blog entry on GridGain's blog. In addition, I'll make sure that each of you have a link to the recording and the slides within 48 hours. So with that said, thank you so much for attending today's webinar. It's called Apache Ignite 2.0, Prelude to a Distributed SQL Database. And I'm pleased to introduce Denis Magda. He's GridGain Systems Product Manager. And with that said, I'll turn the floor over to him. Go ahead, Denis.
Hello, everyone. Thanks, Elisa, for the introduction. So once again, my name is Denis Magda, and I'm a product manager at GridGain and the PMC chair of the Apache Ignite community. And speaking a bit about myself, I joined GridGain in 2015 and became an Apache Ignite committer in the same year. All this means that you are welcome to ask me any tricky questions that come to mind throughout this webinar. And as for this webinar, it will let you look at the Apache Ignite from a completely different angle. Specifically, as the title states, from the angle of a distributed SQL database. And here is I'm not meaning just a distributed in-memory database, as you might assume, but a full-fledged transactional and distributed database that works equally well from memory and disk. However, why do I say that this is the prelude then? And you will get an answer throughout our webinar. So let's move on. As for the agenda, first, we need to take a look and go over all the tremendous changes that happened in Apache Ignite of version 2.0, because that release is completely different from all its predecessors. Right after that, we will dive into the topic of Ignite's virtual memory architecture. This is exactly the new feature, the new component, redesigned memory architecture that allowed us to consider Apache Ignite as a distributed SQL database. And it's essential to spend our time for this topic because, as I said, it's exactly that foundation or baseline that makes it feasible to use Apache Ignite as a full-fledged relational database that works equally well from disk and in memory. And finally, we'll go over all the SQL-related features that are available as a part of Ignite. And some of the features are data modification language and data definition language. Well, speaking about Apache Ignite 2.0, let's speak about Apache Ignite 2.x release, because as I said, Apache Ignite 2.0 built a new path, built a new foundation for the ongoing and future Apache Ignite releases. So if to take a look at this picture, in fact, Apache Ignite is becoming a memory-optimized computing platform that blends a distributed SQL database with an in-memory key value data grid. The computing platform is ACID compliant, is highly available, and can scale out easily to thousands of nodes. And as the slide shows, it can be easily deployed on-premise or on any cloud environment. If you take a look at these, actually all the features and capabilities of Ignite as a platform and framework you see on this picture are already released and available for usage, except for the one that is called Distributed Persistent Store. And this Distributed Persistent Store is shown on this in this section. So in short, that persistent store, that distributed persistent store has been recently donated to the Apache Ignite community, and it's planned to be released in the nearest time. So it will be released in one of the Apache Ignite 2.x releases. And once this happens, once this persistent store is available for the public audience, Ignite will be able to be can be used not only as a in-memory computing platform, not only as an in-memory SQL database, but as I said, as a full-fledged distributed SQL database that works in RAM and on disk. Well, and now let's dive into the details of Apache Ignite 2.0 release. So in general, before we move to the main topic of our today's conversation, to the topic of the distributed SQL database, I want to introduce you all the main features that were developed and that were announced as a part of that tremendous release done by the community. The first one is Ignite Virtual Memory. And we are not going to stop here. We are going to review that memory architecture in details in a couple of minutes. Next, as for the data definition language, we'll spend a bit more time on it at the end of our conversation. But in short, the data definition language is a kind of a new addition, a new big addition to Ignite's SQL portfolio. Before that, as many of you know, Ignite, we were able to use data modification language commands to talk to our Ignite cluster, such as select, update, delete, or insert operations. However, starting with Apache Ignite 2.0, now you can connect to your Apache Ignite cluster and define indexes, alter indexes, drop indexes, define your SQL scheme using well-known and standard SQL commands like create table, drop table, create index, and so on and so forth. Next, the next biggest addition of the Apache Ignite 2.0 release is the machine learning framework, which is called Machine Learning Grid, to follow the naming of the rest of Apache Ignite components. And you know, what's interesting about the Machine Learning Grid is that we had a lot of conversations with our users. And the users tend to ask us, folks, you have a kind of great distributed system that can scale out, that can load balance all the workloads. Why can't we use it for the machine learning? But in fact, the response was kind of similar all the times. We told, you know, actually you can take our data grid capabilities and you can take our compute grid features and build any machine learning algorithms you need. However, it would require our users to dedicate a lot of time for that task. And this is why finally we decided to get down to work and implement a machine learning APIs on top of our data grid and compute grid capabilities. And in Apache Ignite 2.0, the first thing that was released as a part of that component is an implementation of distributed algebra operations. So now if you go to Apache Ignite site and download the release, you are able to write different custom code that will be doing different operations with dense or sparse matrices and other algebra-related operations. In the upcoming releases, you can expect to see implementations of distributed versions for such algorithms like k-means clustering, linear and logistic regressions, and so on and so forth. Okay, switching to our .NET and C++ capabilities. So .NET contributors and committers, they finally released a cool thing that is called plugin system. Now, if you think that something is missing in our .NET library, or you want to implement some custom module that is needed for your specific use case, you no longer need to wait, while this or that feature is to be supported by Apache Ignite community. You can easily take and implement it in your own and easily plug and play, kind of in this sense, plug and play it into the .NET architecture of Ignite. Speaking about C++, finally, and I'm proud of this, our C++ committers and contributors, they were able to find a way on how to execute custom C++ code on remote cluster machines. You might ask, what's difficult about this? Because, you know, actually, when we talk about Java or .NET platforms, it's not a big deal, you know, to execute a custom code like different MapReduce task on your Java or .NET machines, because both technologies do support reflection. And it's easy, you know, to instantiate your class from a bytecode on a remote machine. However, it's not something that is supported for C++ as we know. And that was a kind of a challenging thing for us. And this is why, for instance, there is still no any support for compute grid in C++ available. But as a part of Apache Ignite 2.0, we found a way how to address this issue, how to address this technical challenge. And now you can write your custom C++ code, like filters, compute task, and all this stuff, and send them for the execution to your remote cluster nodes. And if to be more specific about Apache Ignite 2.0, and now in Apache Ignite 2.0, you can define your custom C++ filters for your continuous queries, and that filters will be deployed on your remote nodes and will be executed whenever needed. And in the next releases, we are planning to announce a support for compute grid for C++ and additional features that are missing in that library. And finalizing the list of the biggest and, you know, changes of the biggest features that were introduced in Apache Ignite 2.0, let me speak a bit about the integrations. Eventually, we supported Spring Data framework. That framework, that feature was kind of in the long queue, and a lot of the Apache Ignite users have been waiting it for a long time. And finally, we did it. Now you can connect to your, if you're kind of a fan of Spring Data modules and frameworks, now you can connect to your Apache Ignite cluster by means of Spring Data repositories and interact with your cluster using the APIs provided by Spring. Next, for our Hibernate users, we updated our integration. So now we do provide support for Hibernate of version 5. And at the same time, we extended our streaming capabilities by introducing an integration with RocketMQ. Well, these are kind of the biggest features, the biggest changes that happened to the Apache Ignite 2.0. But at the same time, we did, you know, huge number of performance optimizations and other bug fixes. So, and today, as I told, we are going to talk about one of the biggest thing that was announced in Apache Ignite 2.0, and which is Ignite Virtual Memory, the foundation that made it possible to consider Apache Ignite as a distributed SQL database. So let's move on and look at this virtual memory in more details. Well, don't be scary if you look at the picture that is to the right of the slide, because we are going to do a breakthrough. We are going to split this picture into the pieces and review every component you see right now in more details. But before we do that, I want to ask you questions. What are the benefits, you know, of creating and releasing a new virtual memory? Why did Apache Ignite community need that in general? Because everything looks like to be working, was working pretty well. But in general, Apache Ignite virtual memory architecture resolves the following things that are listed on the slide to the left. First, this is an off-heap page-based memory. Now, all the data is located in off-heap region. meaning that garbage collection, Java garbage collection, done through this region, and that region is fully managed by Apache Ignite virtual memory routines. The first benefit of having off-heap page-based memory is that you can easily exclude noticeable garbage collection poses. And the reason is simple, because if you don't store your data sets in Java heap, then you don't need to spend a lot of the time, for tuning your garbage collection, your JVM and your garbage collection related tasks. Next, the other benefits that were a part of this virtual memory is that now you can control your memory consumption. If we briefly look at this picture to the right, the virtual memory can consist of several memory regions depending on your configuration, and it's up to you to decide how much memory you want to give to Apache Ignite. And it's up to you to decide how you want to share this available memory across your different data sets. Before that, this is something that was not available in previous Apache Ignite releases. You had only one option. You were able, to set the overall, the maximum and the initial size for your Apache Ignite nodes. But right now, this is something that you can easily configure using Apache Ignite virtual memory architecture. Next, the virtual memory frugally uses all the memory that is provided by an operating system, which means that we do care about memory fragmentation. And to be more specific, Apache Ignite memory architecture implements automatic defragmentation of the data. And finally, speaking about the persistent disk storage, which is to be released in the nearest Apache Ignite releases, that memory architecture, which is page-based, allows us seamlessly to integrate with disk. Because, as you know, the fastest way to work with a disk-based drives like Flash, SSD, and different ones is to read by blocks or write by blocks. And this is why it's easier and was essential, to write and operate on pages. And all these pages, if to go a bit forward, all these pages can be stored in RAM as well as on disk in the same format. And and the same page-based architecture is more natural for SQL engines. It's easier for the SQL engines to iterate over the pages rather than on individual cache items or key value items. And this is why, one of the good outcomes of Ignite, or one of the good outcomes after we switched to that virtual memory architecture, was that we could significantly boost our SQL performance. And even more, if you take a look at this picture, you will see that now there is a special data structure, which is called B+Tree. We are going to talk about it a bit later. But in general, that means that B+Tree data structure, it links all the pages, all the data that is stored across your physical memory available, meaning that SQL became a kind of the heart of the overall virtual memory architecture. And for a lot of the scenarios, it kind of drove the workflow on what should be and what shouldn't be supported by virtual memory. Well, let's now take a look at the main components that are shown on this virtual memory diagram. Okay, the first one, that virtual memory is a kind of distributed virtual memory, meaning that you have an access to all of the memory that is available across all of your cluster members, all of the cluster nodes deployed across your network. However, when we'll be talking about this virtual memory throughout this webinar, I will be considering that this is a snapshot of a virtual memory represented on a single cluster node, just for the simplicity. So, and for now, if you take a look at this picture to the right, the virtual memory kind of represents all the memory that is available on this individual cluster node in the RAM and disk. And disk, just to clarify one more time, to be supported in the nearest releases. By default, virtual memory takes all the data available, let's say, all the RAM that is available on your machine. But there is a way to configure and to change this behavior using so-called memory regions. So as you can see from this picture, we have two different memory regions. And the difference is that they can vary in initial and maximum size, and different data eviction modes that we are going to discuss further. Next, every memory region is split into the number of on one or more memory segments. And memory segments, a memory segment is a continuous physical space. So if to be kind of more precise, virtual memory and memory regions are logical structures, are logical terms. But when we start talking about memory segment, this is actually something that is requested and demanded from an underlying operating system. And a memory segment is always a kind of a continuous block or continuous physical space retrieved from your operating system. And next, the memory segment, every memory segment consists of many pages. And the page is a fixed length block. Speaking about the pages. As I said, it's a fixed length block that allows us to use the overall memory available frugally. So all the data, and since it became a responsibility of Apache Ignite to manage the virtual memory, we do automatic defragmentation and compaction, and I'll show you a bit later how it's implemented in Apache Ignite. And in general, there are 3 different types of pages supported by kind of understood by virtual memory. The first one is the data page. And this is actually the page that stores all your data, your key value pairs that you put into the cache. Next, the second type of pages is an index page. And the index page, as the name suggests, stores all the indexes that you define at your application level, or primary keys that are defined all the time right now. Also, an index page, actually, it stores not only index-related data, but also it refers to a specific data page that stores a key value that is sorted in the B+Tree data structure. And the last type of pages, these are kind of system pages, or we call them also meta pages, and they basically are needed for the virtual memory to operate efficiently and properly. For instance, if you take a look at this picture, here is we have one of such a meta page, which is called B+Tree meta page, and this page points out to the head of a B+Tree data structure. Next, now let's take a look at how actually the data page looks like internally. Every data page consists of 4 main building blocks. The first one is a kind of internal system header. It's just needed for the internal usage. And next, there is a kind of your actual data that you put into the cluster, and data offsets. As for the data, data represents just key value records. And for sure, all the records may, and usually they do vary in size. Like here you can see that record 1 is bigger than record 2 and record 3. And all of the values are added to the right of the data page. So the values, it grows in the direction from right to the left. And also we have to track so-called data offsets. or links, you can call them this way. These data offsets point out to specific data records located in this page. Like a data offset for record 1 is located here. Here is we have data offset for record 2, and so on and so forth. And all these data offsets, they are actually stored and used in different internal structures of virtual memory, such as B+Tree or free lists, and so on and so forth. It means that if someone, for instance, if your application wants to get some data, then at some point of time, we need to get a data offset to a specific record in your data page, and this data offset is stored somewhere in B+Tree data structure. Well, now let's take a look at the defragmentation, how the defragmentation is implemented. Let's assume that we decided to remove, that your application decided to remove key value record 2. Once this happens, we'll have two different free kind of empty holes in our overall page, like you see here. At the same time, but all this means that virtual memory still will think that there is much more memory available. The only difference is now that the free space is no longer kind of a continuous space inside of your page. And for instance, when your application tries to insert a value that is bigger than the biggest free space inside of the page, then the virtual memory will automatically kick off the defragmentation routines or compaction routines. Specifically, a value 3 in data set of 3, at some point of time, that will be shifted to the right and to the left. And right after this happens, we can easily insert our next big value into this page. And this is how this compaction on defragmentation works in reality in Apache Ignite virtual memory. And we do know that the data eviction, we do know that kind of all the RAM that is available is not endless, right? And now, for instance, if you want to enable some data eviction policies, for instance, you can fit all the data in memory by some reason, then you can enable so-called data eviction page-based eviction modes. We do support 2 page eviction modes. The first one is random LRU, and then other one is a kind of an improvement, an advanced version of the following. The whole idea of those 2 page-based eviction modes is that every page we have in our virtual memory has a timestamp associated with it, a timestamp of the last time a page was accessed. And then when you run out of memory on an individual node, and here is I mean in a physical memory, kind of RAM, then the virtual memory will remove the least recently used pages. And we will be removing pages with all the entries that are stored inside. However, here is, but if you use, for instance, kind of our persistent storage that is to be released pretty soon, then the data will not be lost because it will be located on disk. Or even if you used some other third-party storage like a relational database, then this data will already be persisted in that database. So this is needed only for the scenarios when you have a scarce RAM resources. And finally, but if you want to, as I said, the virtual memory is no longer, it's an off-heap memory, meaning that all the data is stored outside of Java heap. But there is an option to enable so-called unheap caching for your records or cache entries stored in off-heap region. And this is kind of sometimes it used, for the scenarios when you do a lot of read operations on your server nodes and you don't want to bring entries from off-heap to Java heap all the times. And if you enable this on-heap caching, which is optional and turned off by default, then you need to enable kind of LRU, FIFO, or sorted eviction policies for entries, for the entries that are stored in that on-heap caching layer. And if you take a look at this configuration black, here is you will see how you can actually define a memory region. To define a memory region, we need to set special memory policy configuration. And here is we're saying that the name of this memory region will be 20 gigabyte region eviction. The initial size will be 5 gigabytes, and the maximum size will be 20 gigabytes of that region. And we enabled random to LRU eviction mode for that space. Pretty easy. Okay, now let's take a look at the heart of our virtual memory architecture, at the B+Tree data structure. So actually, B+Tree is a self-balancing tree data structure that keeps data sorted and allows searches, sequential access, insertions, and deletions in logarithmic time. And the B+Tree, once again, is a central part of the whole Ignite virtual memory architecture, because as we saw from the previous diagrams, all the data that is stored in virtual memory is located in random locations. So all the index pages, all the data pages, they will be placed depending on the current state of the art. So depending on whether you have, there is no any logic. But if you need to link all these randomly allocated pages in some logical structure, then you need to use data structures like B+Tree. And B+Tree works over the data that is in memory and that is on disk. And if you take a look at this picture to the right, you will see that actually the B+Tree links altogether, links and sorts all the index pages that are stored, located in your physical memory. Let it be RAM or disk. And as for the indexes, if to talk a bit about the indexes, we do support sorted index. These are the indexes that you define at your application level using data definition language or other approaches available in Apache Ignite. Or the second type of index is called hash index. And actually, it's the same hashing. It's the same sorted index, with the only difference is that it's used for your primary keys. For all these values that you try to put into your cluster, they have a key, and that key will be considered as the primary key. And for all the primary keys you have in a specific cache, we will maintain and define an individual B+Tree data structure. And all the sorting of the primary keys will be based on the hash code returned by a key. Well, knowing and keeping this in mind, knowing that B+Tree is a kind of central part of the virtual memory architecture. Now let's take a look at the execution flow of a basic and the simplest cache get operation that you usually can do in your application code. Or for instance, you can execute, instead of cache get operation, you can execute the simplest SQL query like select everything from cache where key A equals something. It will be executed in a similar way. So, okay, here's where our application tries to get a value for key A. First of all, as before in previous Apache Ignite releases, we need to find out a primary node for this key. So we are going to use affinity function to find out the primary node, and we will send a remote kind of network request to that node, asking for the value for this key. Once the node receives such a network request, it will try to find out a memory region the cache belongs to. So the beauty of the memory regions, right, as we discovered, the memory regions allows us to define memory spaces of different characteristics, and then you can assign every cache to a specific memory region you defined in your configuration. And next here is we will find out the memory region for our cache. Once this happens, we need to find out the B+Tree data structure that sorts and links all the primary keys. and our key A will be a part of this B+Tree data structure. Right after that, we will take a kind of hash code of key A, and we'll do a lookup in our B+Tree. As a result of this lookup, B+Tree will return you a specific index page. And that index page will contain a reference to our data page. And in addition to the reference to the whole data page, it will contain an offset to the value, to the key value record inside of the data page. And right after that, the virtual memory will pick the data page and grab a specific value using offsets stored in the index page. And you and your application will get the whole value back. Good. Okay, on the previous slide, we explained how to look up a value inside of the virtual memory, relying on the B+Tree data structures. However, how does the virtual memory know where to put a new value? In fact, to support this scenario, Ignite uses a special data structure called free list. Basically, a free list, if you take a look at this picture, a free list is a doubly linked list that stores references to pages of approximately equal free space. For instance, there is a free list that stores all the data pages that have up to 75 free space, or there is a list that stores all the index pages that have around 25% capacity left. And free list data structure is essential for update operation, because the goal of the virtual memory, as I mentioned, is to use our RAM and disk frugally. And this is why when you try to insert a new value into your cluster, the free list will try to return you a page with the minimum space needed to fit that specific value. And actually, this helps us to reduce fragmentation and helps us to, to lower compaction activity. Because we do know that the fragmentation is unavoidable in general, especially if your cluster is up and running for months, years, and more. But if you use your memory frugally, then you can, reduce all the compaction or the fragmentation activity significantly. And this is why the free list is a kind of essential part of our virtual memory architecture. And now let's quickly look at the execution flow of the basic put operation. It can be kind of cache put operation, or it can be in SQL insert operation, whatever you like more. So again, we need to find out a primary node. We need to send a network request to that node, and once the request is received and processed, we'll find a memory region the cache belongs to. Then nothing changes here. We need to find the B+Tree for primary keys. Inside of this B+Tree, we need to find a position, a unique position for our index page that will hold the new key and value. And once we find that position, and if there is already an index page at this position, and if we can add additional extra index to that index page, then we will do it right away. Otherwise, if the index page is missing, then we will do a call, we will call our free list that will return an index page with the minimum space needed to fit our new index. And later on, we need to add our data into the data page. And if we will call our free list to get the page with the minimum space needed. And once the page is retrieved, we will put our entry, we will put our key a val a record into the data page, and we'll do compaction and defragmentation of the pages if needed. Okay, that's all. So guys, that's actually all about, these are essentials you need to know about the new virtual memory architecture. So, and this is how it works, and this is how you Ignite leverages from it. Now let's briefly look at the virtual page memory secondary storage, which is our disk storage that is to be released in the future Apache Ignite releases. Again, what are the benefits and what are the main features of that storage? These are distributed and transactional storage, which is ANSI 99 compliant. And literally, it allows to expand virtual memory to disk. So the data will be stored not only in RAM, but will be stored on disk. The only difference, so one of the main difference between Ignite's virtual memory and virtual memory you have in operating systems like Linux or Windows is that in case of with Ignite, if a page is stored in RAM, it will be always stored on disk, meaning that disk is always to be considered as a superset of all the data you have. The scenario when the data is located in RAM but is not located in disk is not possible with Ignite's virtual memory architecture. So the disk is always a superset of the data you have in RAM. But at the same time, again, all the data that is stored, the pages that's stored in RAM and on disk, they are stored in the same format that avoids us doing all the complex serialization and deserialization between RAM and disk. And one of the, in addition to the advanced SQL capabilities, so because with this architecture, you are able to execute SQL queries over the data that is both in RAM and in disk, but also you can achieve so-called instantaneous restarts of your cluster. Meaning that if by some reason whole your cluster went down, then you don't need to warm up all your RAM once your node's up and running. Your applications can start interacting with your cluster once all the nodes are interconnected. Because the data will already be located on disk, all the indexes will be on disk, and you are good to go. You don't need to wait while all the data will be preloaded in RAM. And again, this is to be released in the nearest Apache Ignite releases. Okay, that's our virtual memory, right? That's the complete picture. Here as we see kind of memory regions, memory segments that represent physical space available that is split onto different pages. And all these pages are linked together by B+Tree data structure. That is a central part of the overall memory architecture. And we do have another important data structure, which is free list. Well, and based on this architecture, specifically on this architecture, we were able to, do advanced improvements in Apache Ignite SQL engine. And this specific architecture allows considering Apache Ignite as a distributed SQL database. And now let's take a look at the main characteristics, probably the main features of that distributed SQL database. First, it's no longer about a single node. It's not about a monolithic platform, right, deployment. So if you take a look at this picture, all the data is spread out across a cluster of machines you have, data and indexes. The data, if you want to use, if you want to use the persistence, if you want to use Ignite's persistent disk store, that you are required to enable it. But by default, the data is stored in RAM, and the disk is activated only if you need it. The SQL database is ANSI 99 and is SID compliant. It's always highly available, and it can scale to thousands of nodes. And as we know, it can be easily deployed on premise, cloud, on different containers like Kubernetes, Docker. It's up to you. There are no any limitations. Speaking about the APIs available. So it's essential for every database to support well-known standards and drivers, and we do support ODBC and JDBC driver. And in addition to the standard interfaces, we provide native libraries for Java, .NET, and C++ languages. All these wide support of different drivers and technologies mean that you can connect to your cluster literally from many different languages and technologies. Let's say from Java, .NET, Python, PHP, different tools and different management and monitoring consoles. Well, speaking about the data modification language. So first, Data modification language, for those who are not aware what's this, actually it defines a set of standard SQL operations that have to be supported by a relational database, by the database that kind of SQL enabled. And first command is kind of select operation, right? We want to select data stored in our cluster. And here is, again, I just want to emphasize one more time that the engine is NC99 compliant. You can, and you are kind of empowered with the capability not just to execute simple queries, but you can do distributed joins. You can group your data, you can aggregate your data and sort your data. Everything is available. All this means that actually Apache Ignite's SQL engine do support ad hoc SQL queries. And as we already know, all the SQL capabilities are based on the virtual memory. And as we know, trying to make a conclusion, the data is stored in the form of pages in a heap region or on disk, and on disk if you enable the latter. Next. And here is a coding example, a quick coding example. Here you can see how you can use, let's say to the left, you can see how to execute kind of distributed join for personal organization datasets stored in your cluster from Java. And on the other side, we show how to update the data stored in your cluster using our DBC driver. And actually, this operation is being executed from PHP language, as far as I recall. So from PHP, for instance, you can connect to the cluster using a DBC and execute an update statement like that. Well, that was about the reading, about the data read. So, but what's about the data modification? Nothing different. So again, we do support all the standard operations like insert, update, delete, merge, and they are exposed over DBC and JDBC drivers, as well as our native Java.NET and C++ APIs. And for instance, to the right of the slide, you can see how to update a record in your cluster using update statement from Ignite's C++ application. Well, and finally, guys, we know that it's essential, right, to support all the DBC, GDBC drivers and provide some specific interfaces for native interfaces for technologies and languages like Java.NET and C++. But sometimes we simply need, to connect to our cluster and to execute some sample queries to validate our data sets, to check that a specific query is well written and well defined, meaning that all indexes are properly set. For this scenario, you can use different monitoring tools or different SQL consoles. For instance, here we have Apache Ignite community has its own Apache Ignite web console tool. And on this slide, you can see how it's easy to connect to a cluster of your Apache Ignite nodes and execute ad hoc SQL queries, including read and update operations. At the same time, for instance, using GDBC driver, you can easily connect from tools like Apache Zeppelin and validate or check out all your SQL queries from there. And finally, if you're doing a kind of advanced data analysis, for instance, you can use a tool like Tableau, which can easily connect to our cluster using a DBC driver. That's it, no difference. And the last part of our kind of distributed database I plan to talk about is a data definition language. So this is So this is this is the last addition to our SQL portfolio. And finally, now it helps you as a user to work with Ignite as a true SQL database, because having DDL support, you are not longer stuck to XML or Java.NET based configuration. Actually, the goal of this development is, to give you a way to connect to the cluster, Apache Ignite cluster, and define your schema, alter your schema, create and drop indexes using standard DDL statements like create table, drop index, and so on and so forth. And the first thing that is already supported and announced in Apache Ignite is a kind of a support for the create and drop indexes commands. And you can do this in runtime without a cluster restart. And that was one of the most anticipated feature that was requested. I think that from the very beginning, SQL capability were introduced in Ignite. And now we know that a lot of our users, they are happy and they're welcoming this feature. Like if you take a look at this picture to the right, all these fans have been anticipating this kind of a concept of that rock star, and a lot of our Apache Ignite users, they kind of met and welcomed this feature in the same manner. And later on, in Apache Ignite 2.1, they are going to release additional features. So you will be able to create and drop your schema, a SQL schema, and later on you can expect more and more features related to the data definition language support in Ignite. Well, guys, that's all for today. So now I would encourage every of you to go to ApacheIgnite.com, download Apache Ignite 2.0 release, give it a try. Try to use Apache Ignite as distributed database, and we highly we welcome you to provide feedback and share your experience with us, because it will definitely help us, helps Apache Ignite community to make the database the best one. So thank you.
Okay, Denis, we have some questions from the audience. And audience, just to refresh your memory, I will make sure that everyone here gets a link to the recording and the slides. So fear not, I'll get those to you in the next 24 to 48 hours. I'm usually pretty quick about turning it around. Okay, so your first question is, let's see here. Does this also involve support for ORM functionality?
ORM, you mean that you can use different frameworks like Hibernate, Spring Data on top of it. So virtual memory is about internals, right? So we don't care what you're using in the application level. You can use basic key value operations. If you talk about the virtual memory architecture, you can use SQL. You can use different ORM tools or frameworks, right? Spring Data, Hibernate, whatever you prefer to use. So virtual memory is all about the internals and what it gave us. What are the benefits of having the virtual memory?
And I apologize, the question had a follow-up. So for example, would there be a persistence framework that takes care of boilerplate stuff like DTO, model, and SQL generation?
Actually, so I don't know. So actually, SQL, as for the SQL, we do probably it makes sense to discuss this on the user list so that I can get more kind of details around this, because we don't plan to reinvent any kind of SQL generation stuff for now, because you just need to write SQL on your own. But in any case, if you know or you kind of feel that it's kind of something that is needed, it makes sense to go to the Apache Ignite community and to discuss it with wide audience. But for now, as far as I recall, we don't have any plans to support any SQL generation stuff.
Okay, next question. How long will we be waiting for a new edition of the book? Current edition talks about version 1.7 of Ignite.
Actually, I know the author of the book, and I do know that he keeps an eye on all the features that are happening to Apache Ignite project. And I do believe so that pretty soon, once this, we released 2.0 only kind of less than a month ago. And I do believe that he will be able to update, to refresh the book. I hope in the nearest month or so. I don't know. We just need to talk to him.
Okay. Whoops, here comes more. Okay, he wrote, thank you. Are there any other questions from the audience? So far, that's pretty much it, but I'll give you a few seconds to add more. So we're in the process of adding quite a few new webinars to our calendar. We have a couple coming up that are pretty exciting. Our technical evangelist is going to be doing one on ACID transactions in July. And there's going to be a whole bunch of stuff related to our new releases of software coming out pretty quickly. Will be published pretty quickly in terms of webinars. So I encourage everyone to come back and take a look at the schedule. Plus, as you know, I will send you out newsletters letting you know when the next webinars are and what their topics are. Okay, so with my babbling, there were a couple of questions. Does SQL Query Update Seamless integrate with Key Value API?
Yeah, actually, you know, if we talk about select operations, select commands, they are executed right away. So we are integrated with H2 database, and we use H2's query execution and optimization plans to execute our select queries. But as for the update operations, finally they are turned into a set of key value updates.
Okay, next question. How does failover work with virtual memory when a node goes down?
The same way as before, so nothing changes. Like everything that was supported in Apache Ignite 1.x works the same. We do support rebalancing all the data. Like if to speak about the virtual memory, every virtual memory on an individual node, it will store primary datasets for which the node is primary one, as well as datasets for which the node is backup one, meaning that if some other node goes down, there will be backup copies stored across different cluster nodes in virtual memory of those nodes.
Okay, next question. Is there any support for versioning of the schema in Ignite?
Yeah, it is. So it's versioning. You can even now and even prior to the DOE, you were able to connect to your cluster and change kind of fields and schemas of your business model objects, and that was supported, relying on binary marshaller. Next, as for if to speak about the data definition language, now you can change indexes, add new indexes, or drop indexes in the runtime without a cluster restart. And also in the nearest time, the community will support alter table commands for the scenarios when you need to, add new fields or new columns to your specific table defined in the cluster.
Okay, we have time for one more question. And like I said, I will be sending all the questions to Denis so he can read the ones that were missed. The last question that we can ask today is, does auto defragmentation hold off query update or happen in the background?
So there are two modes as far as I recall, but I can clarify it. We can clarify it from the virtual memory architectures. By default, it can be, there are two modes, eager one and the lazy one. The lazy one is that when the defragmentation happens only when an entry is supposed to be stored in a specific page, and the page is fragmented. And at that time, the defragmentation of the page will happen. At the same time, I do know that there is a special mechanisms that is kicked off in background, and to give more kind of details on when it's kicked off and what is a kind of kind of a trigger for that situation. I think that this is something that can be discussed on the dev list, but it's definitely supported. We just need to find out what's the trigger for the compaction or defragmentation in background.
Okay, well, this brings us to the top of the hour. Denis, thank you for a great, informative webinar. The feedback is really positive here. And audience, always we enjoy your participation and hope to see you in future webinars. Everyone have a great day or evening, depending on where you're calling from. And Denis, thank you again.
Thank you, everyone. Hope to see you soon. Bye.